Now this is something only mathematicians would do. They want to know if the interest had continuous compound interest. So what does it mean if you have continuous compound interest versus yearly versus monthly versus daily? This is, you could do every second. This is like every moment, every day, the smallest of unit of time possible. And basically what that means is n goes to infinity. The number of compoundings per year goes to infinity. And so only mathematicians would think of this, so a continuous compound interest. All right, and we're going to try and approximate the continuous compound interest. So we got two cases here. So both of them, we're going to have an initial value in the savings account of 1. And then this interest rate is going to be 5%, and this interest rate is going to be 100. And we want to try and figure out what happens as n goes to infinity. Little problem with n goes to infinity, we can't plug in infinity and actually calculate it. Right, so if we plug this in, it's p naught times 1 plus r over n to the n. If we plugged in n equals infinity, then we get r over infinity, which is kind of like 0, but then we get to the infinity power, and so who knows what's going to happen there. We can't just, figure it out. So instead we're going to approximate it. So we're just going to try n is equal to 100,000. Right, fairly large number. So if we plug that in, we have 1 times 1 plus 0.05 over 100,000 to the 100,000 power. That's probably a little difficult for your calculator. You're going to have to use something like Wolfram Alpha to do this. It's more accurate. But if you do that, then what pops out is, I'll say approximately, it's 1.0512718, and then a bunch more stuff. And then the funny thing is, if you calculate e, and I'm going to e to the 0.05, which is approximately 1.0512719, ... And so there's actually something, e has something to do with this problem. So somehow e is defined by this. Somehow this is a way to calculate e. Not a very good way, it looks like, because you have to do 100,000. That's a very difficult computation to do, and you got, not that many digits of accuracy. But it does look like e has something to do with this. Well, okay, so this is e to the 0.05 power. Well, what if we just want e by itself? That would be e to the 1. And that's why I've written here, instead of using a rate of 5%, if we use a rate of 100%, then that's going to end up with an approximation for e to the first power. So just the number e. So again, we can't plug in n equals infinity, so we're just going to try n is equal to 100,000 again. And we're going to calculate that. Right, again, it's going to be 1 times, this is 1 plus, we have 100% interest rate, so we just have, kind of 1.00 over 100,000 to the 100,000 power. If you plug that in and do that, this is approximately 2.71826 ... And if you calculate e to the first power, right, so that's just e, that's approximately 2.71828 ... So not a whole lot of significant digits here, not a whole lot of digits of accuracy, especially given we had to use 100,000. But this is why mathematicians were a little interested in this, and it's not just a silly problem, not a silly math problem. Homework problem. There's a mathematician called Bernoulli, and Bernoulli actually studied this. It was important enough that he devoted some time to investigating what was going on here. And so it's not just something that some person who wrote a math textbook came up for your homework. It was actually important in mathematics hundreds of years ago.